All right, we're going to take a look at limits. All right, let's look at this function right here. We have y equals sine of x over x. And think about what happens when x equals 0. Well, sine of 0 is 0. And if we let x equals 0, we have 0 over 0. And we want to be really careful here. The statement 0 over 0, we definitely don't want to put an equal sign there because nothing can equal 0 over 0. That's it's kind of a nonsense statement. So I'm going to cross that out. I want to make that really clear that this does not equal 0 over 0. We would say that it's undefined. Okay, now, despite the fact that it's undefined, that means that there is no value. When x equals 0, y doesn't have a value. But we can still talk about what the function is approaching as x approaches 0. So we're going to investigate the graph. Create this graph, and it looks, just on first glance right there, to be approaching a y value of 1 as x approaches 0. You can zoom in. Zoom trig just makes it so that the window goes from 0 to 6.28. That's 2 pi. We can look at a table. We can see here that it's undefined when x equals 0. We can change our table step to 0.1. If you really wanted to get deeper into this, you could go with 0.01, 0.001, and you can see that those values get closer to 1. So the values get really close to 1, but the values never actually equal 1. Okay, so when we talk about the limit of a function, we're talking about the value that it's approaching. What's it getting close to, even if it never gets there? It could get there, but it might not. So we would say the limit of f of x equals sine of x over x as x approaches 0 is 1. So the function approaches a y value of 1 as x approaches 0. And here's how we write that with limit notation. So if we have the limit of a function as x approaches c, we have limit as x goes to c of f of x equals L. With that example we were just looking at, the limit as x goes to 0 of sine of x over x equals 1. Now for this class, we haven't proven that this is true. We've investigated it and we've kind of confirmed to ourselves we think it's true. For now, we're just going to accept that as fact. So whenever this limit shows up, you're able to go ahead and just use that. Okay, and important to remember that the limit of the function refers to the value that it approaches, not the actual value. So the limit and the actual value could be different values, or it could be that the actual value just doesn't exist. So let's take a look at this right here. F of 2, so go over to x equals 2. We can see that the dot occurs there at 1, so that's where the point actually exists. But the limit as x goes to 2 is 2, because the function from both sides is approaching 2. So the limit is what the function's approaching, not what it is equal to. Okay, we can add, subtract, multiply, divide. We're going to have all those manipulations of limits. If you can look at page 61 in your textbook to see a little more info on that. And it's important to understand that for a limit to exist, the function has to approach the same value from both sides. We can talk about one-sided limits, which would be what's happening as we approach a value from the left or as we approach from the right. Okay, so looking at x equals 1, the limit as x approaches 1 from the left-hand side. Notice that little negative superscript. That means we have a left-hand limit. We're approaching from the left side. So as we go along the curve from the left side, approaching x equals 1, the function approaches a y value of 0. From the right-hand side, the function approaches 1. The actual value of the function is 1. But we would say that the limit as x goes to 1 of f of x does not exist because the left and the right-hand limits are not the same. At 2, the left-hand limit is 1, the right-hand limit is 1, the value of the function is 2, and we would be able to say that the limit does exist, the limit equals 1, because the left-hand and the right-hand limits are the same. Remember, the limit does not depend on the value of the function. At 3, the left-hand limit is 2, the right-hand limit is 2, the value of the function is 2, so we would say that the limit as x goes to 3 of f of x is 2. And we could make one more statement here, which is to say that the function is continuous. A function is continuous if the limit and the value of the function are equal to one another. So here's reiterating that definition of continuity. Continuous at a point x equals a if the limit as x goes to a of f of x equals f of a, if the limit equals the true value. Okay, we're going to look at how we can try to evaluate limits. First thing to try is just substitution. Plug in the number. If we know the behavior of many types of functions, polynomials, trig functions. If your function is continuous, you can just try substituting the number in. So here's a polynomial. We know polynomials are continuous. Plug in x equals 0, and we get 7, so the limit is 7. We know that this function right here, this rational function, is undefined when x equals -1, but defined everywhere else. So if we plug in 2, we get -1. So since these are continuous, we're allowed to just substitute. Now if I try substituting here, plug in 3, and I get 0 over 0. Again, cross that out. We don't want to ever say 0 over 0 because that's not a meaningful statement. So we'd say that this is undefined. But this may actually have a value, so let's find out. If we factor the top, we can cancel the common factors, now plug in 3, and we get 1. So this function does not have a value. It's undefined when x equals 3, but the limit as x approaches 3 is 1. Now, if you want to investigate this on your calculator, you can feel free to graph it. It turns out to just be the graph of a straight line, y equals x minus 2, that just has a hole when x equals 3. And sometimes simplifying algebraically doesn't work. There's nothing we can do here to simplify. If we plug in 0, we get 0 over 0. And we're actually going to look at this later on in the year to see how we can evaluate limits such as these. We'll have a nice handy tool that we can use, but we need to learn a few things first. Okay, take a quick look at the sandwich theorem. Okay, take a moment to read through this right here, and then we'll talk about what this actually all means. So the big idea here is the function f is, we know, is always greater than g and always less than h. And if the limit of g and h are both the same, well, since f is always between them, it must approach the same limit as well. So if we have a limit that's maybe really complicated that we can't figure out directly, if we can figure out a function that's less than another function that's greater than, if they both approach the same value, then we know that our function must approach that value as well. Okay, so we want to look at the limit as x goes to 0 of x squared sine of 1 over x. Well, we actually want to show that that equals 0. Well, if we were to just plug in 0, we would have 0 times sine of 1 over 0, which is undefined. So we can't show this by substitution. But we do know the behavior of sine. Sine goes from 1 to -1. So if we take x squared times sine of something, at most that's going to be 1. So we know x squared sine of 1 over x has to be less than or equal to x squared. And since sine goes down to a minimum value of -1, we know that x squared sine of 1 over x has to be greater than or equal to -x squared. So we know that x squared sine of 1 over x is greater than or equal to -x squared, less than or equal to +x squared. So we take the limit of these. The limit as x goes to 0 of -x squared is 0. Limit as x goes to 0 of x squared is 0. Since x squared sine of 1 over x is always between those two, by the sandwich theorem we can state that the limit as x goes to 0 of x squared sine of 1 over x has to be 0. Now let's put that into our calculators and see what we end up with here. So we're going to graph x squared, -x squared, and the function we're trying to figure out. You can see the graph of x squared, the graph of -x squared. This is pretty cool right here. Watch x squared sine of 1 over x, always between these two, and it gets squeezed through or sandwiched through, and we can see clearly from this that the y value is approaching 0.